The James Webb Space Telescope was built to look farther than any telescope before it. But in just a few short years, Webb has already gone too far, at least in the sense that what it's finding doesn't match what we thought was possible. When astronomers first trained Webb on patches of sky that look empty to the human eye, they expected to see faint, primitive galaxies, tiny clumps of stars just starting to come together. Instead, Webb revealed bright, massive galaxies that seemed far too mature for such an early universe. Some of them existed when the cosmos was only a few 100 million years old. That's like walking into a kindergarten class and finding full-grown adults sitting at the desks. And it isn't just distant galaxies that defy expectations. Webb is uncovering oddities in our own solar system. Mysterious, dark beads floating in Saturn's atmosphere. Chemical signatures on Pluto's moon that shouldn't be there, and even hints that distant dwarf planets might be more active than anyone imagined. The deeper Webb looks, the stranger things become. Every surprising image, every unexpected chemical fingerprint is forcing scientists to rethink how galaxies grow, how stars form, and even what's happening in the cold outer reaches of our solar system. So let's break down the most shocking things Webb has uncovered so far and why they matter for the story of the universe. The James Webb Space Telescope is sometimes described as a time machine. That phrase gets thrown around a lot, but it isn't just hype. When scientists say Webb can look too deep, what they mean is that it can reach so far into space that it starts bumping up against the limits of our models. To understand why, we need to unpack what makes Webb different from any telescope that came before it. Start with the basics. The Hubble Space Telescope gave us breathtaking views of the cosmos for over 3 decades, but Hubble sees mostly invisible light and a bit of ultraviolet. That's perfect for catching starlight and glowing gas, but not so great for really distant galaxies. Why? Because the universe itself stretches light as it travels. The farther away a galaxy is, the longer its light has been travelling toward us. Over billions of years, the expansion of the universe stretches those wavelengths into the infrared. By the time the light from a galaxy born just a few 100 million years after the Big Bang arrives here, it's no longer visible, it's deep in the infrared. That's where Webb comes in. Its 6.5-metre gold-coated mirror collects more light than Hubble ever could, and it's tuned almost entirely for infrared wavelengths. Infrared astronomy isn't just about distance, it's also about clarity. Infrared can cut through cosmic dust that blocks visible light, revealing stars forming inside thick clouds and structures that would otherwise remain hidden. So when scientists say Webb can look deeper, they mean 2 things at once. It can detect fainter objects than ever before, and it can see farther back in time than Hubble. Looking back in time is not science fiction. It's simply the reality of light travel. If an object is 10 billion light years away, we see it as it was 10 billion years ago. Webb pushes that boundary to galaxies forming within the first few 100 million years of cosmic history. Now add another tool, gravitational lensing. This is one of nature's own tricks, predicted by Einstein's theory of general relativity. A massive galaxy cluster sitting between us and some distant background galaxy can act like a magnifying glass. The cluster's gravity bends and stretches the light, brightening objects that would otherwise be invisible. Webb has already taken advantage of this effect, staring through these cosmic magnifying glasses to spot galaxies that are smaller, fainter, and farther than anything seen before. Without Webb's sensitivity and resolution, those lensed smudges of light would just be background noise. The idea of a deep field comes from this technique of staring for long periods into a tiny patch of sky. Hubble's famous deep field showed thousands of galaxies in what looked like an empty spot. Webb repeats that experiment, but in the infrared, reaching even farther. In those deep fields, Webb doesn't just see galaxies, it sees them shockingly well-formed, in numbers that surprise theorists. But let's pause here. What does it mean to say Webb looked too deep? After all, scientists wanted to see the early universe, isn't that the point? The shock comes from what Webb is actually revealing when it peers that far. According to decades of cosmology, the early universe should be a place of slow build-up. Tiny density fluctuations left over from the Big Bang collapse under gravity, gas cools, stars ignite, and eventually galaxies form. In the first few 100 million years, those galaxies should still be small, dim and chaotic, cosmic toddlers just learning to walk. Instead, Webb shows galaxies that look far too bright, too massive, too structured for their age. Some of them appear to contain as many stars as the Milky Way, even though they formed when the universe was less than 5% of its current age. It's as if you expected to see saplings in a young forest, but instead found towering oaks already standing. That disconnect between expectation and observation is what makes Webb's depth feel almost too deep. It's not that Webb is malfunctioning, it's that reality itself isn't matching predictions. And this isn't the first time astronomy has hit such a wall. When Hubble was launched in the 1990s, it too surprised scientists by revealing that galaxies were forming earlier and faster than models allowed. But Webb is extending that problem to an even earlier time, almost right up to the cosmic dawn. Each surprise forces astronomers to refine their theories. Maybe star formation is more efficient than we thought. Maybe feedback from black holes and supernovae, which can regulate galaxy growth, behaves differently in the young universe. Or maybe our understanding of dark matter, the scaffolding that galaxies build themselves around, needs a rethink. Beyond galaxies, Webb's deep vision also works inside our own cosmic neighbourhood. Infrared lets it probe atmospheres of planets and moons, detect heat from cold objects, and pick up chemical fingerprints invisible to other telescopes. That's why Webb can detect strange features in Saturn's atmosphere, or unexpected compounds on distant icy worlds. Even here, looking deep means revealing layers that are usually hidden, peeling back the surface to see the processes underneath. To appreciate how radical Webb's capabilities are, consider the scale of light collection. A telescope's power depends heavily on the diameter of its mirror. Webb's is about 2.7 times larger than Hubble's, but the light gathering area scales with the square of that diameter. That means Webb can collect over 6 times more light. Combined with instruments designed to work in the infrared, it can spot galaxies that are literally 100 times fainter than what Hubble could catch. And because it operates far from Earth, parked at the L2 Lagrange point about 1.5 million kilometers away, it avoids the heat and glare of our planet. Its massive sunshield keeps it cold enough that its own heat doesn't swamp the faint signals it's trying to detect. This sensitivity comes with trade-offs. Infrared detectors must be kept extremely cold, which is why Webb can't be serviced like Hubble. But the payoff is extraordinary. Webb can look back over 13.5 billion years, nearly to the Big Bang itself. For astronomers, that's like opening a photo album and suddenly discovering snapshots from the very first pages, where you thought nothing had been recorded. And yet, as with any powerful new instrument, the data come with surprises. Webb isn't just filling in missing details, it's forcing us to confront inconsistencies. Some galaxies look too old, some chemical signatures don't fit our theories. Even nearby planets and moons appear stranger under its gaze. When we say Webb looked too deep, what we really mean is that it has gone far enough to make us uncomfortable. It has pushed into a regime where the universe doesn't behave exactly as the textbooks predicted. That discomfort is not a failure. It's the very engine of science. But it's also why the headlines can sound so dramatic. Every deep field image Webb takes seems to throw up new puzzles. So now that we've seen how Webb can see so far, the real story begins with what it actually found out there. And the first shock came not from a strange chemistry or planets in our backyard, but from the very first galaxies, the oldest starlight the telescope could possibly reveal. When astronomers first switched Webb on and pointed it at the deep universe, the expectation was modest. They hoped to catch glimpses of the earliest galaxies, tiny, irregular clouds of stars just starting to assemble. What Webb actually delivered was something far stranger. Massive, bright, well-structured galaxies that seemed to have no right to exist so soon after the Big Bang. One of the first big shocks came from a galaxy now labelled JD's GSZ 14-0. Webb detected it in 2023 during a survey of faint galaxies in a region of sky called the Good South Field. By measuring its redshift, how much the universe has stretched its light, astronomers placed it at a time only about 290 million years after the Big Bang. That's barely 2% of the universe's current age. And yet, this galaxy wasn't a dim little smudge. It was bright enough that it must have been forming stars furiously, converting gas into starlight at a pace much faster than expected. Another case, announced in 2024, made headlines under the nickname Zhulong, meaning torch dragon in Chinese. This object isn't just early, it looks structured, with a disk and even hints of spiral arms. It existed about 900 million years after the Big Bang, yet already had features similar to our Milky Way. Spiral galaxies are supposed to take billions of years to form, slowly settling into their iconic pinwheel shapes. Geelong seemed to have pulled it off in less than 1 billion. These weren't isolated finds. Webb's surveys kept turning up more of them. Galaxies that were larger, brighter, and more numerous than most cosmological models predicted. The problem became known informally as the too many, too soon puzzle. In simulations, galaxies in the first few 100 million years should be tiny and rare, but Webb was finding them in bulk, some containing as many stars as the Milky Way. To see why this is such a headache, consider how galaxies grow in the standard model of cosmology. Structure in the universe begins with dark matter, an invisible form of matter that outweighs normal matter by about 5-1. In the early universe, dark matter clumps under gravity, forming halos. Gas falls into those halos, cools and forms stars. Over time, small halos merge into bigger ones, and galaxies assemble through countless collisions and accretions. That process is messy and slow. By 300 million years after the Big Bang, we expected little more than embryonic star clusters. Yet Webb shows mature galaxies already shining. That suggests one of several possibilities. Star formation was hyper-efficient. Gas might have collapsed into stars at an accelerated rate, perhaps due to conditions in the early cosmos that we underestimated. Feedback mechanisms were weaker. Normally, when stars form and then die in supernovae, they blast gas back out of galaxies, slowing down growth. If early galaxies lost less gas, they could have grown faster. Dark matter behaves differently than we thought. Our models assume cold, collisionless dark matter that structures galaxies in a certain way. If dark matter interacts more strongly, or has different properties, it could alter how fast galaxies assemble. We're misinterpreting the data. It's possible that some of these galaxies only look massive or bright because of unusual star populations, like an early generation of super bright stars, or because lensing's boosting their apparent brightness. One especially interesting angle is the idea of population 3 stars. These would have been the very first stars in the universe, made of only hydrogen and helium. With no heavier elements, they are thought to be extremely massive and short-lived, burning hot and bright. If some of Webb's too bright galaxies are lit by clusters of population 3 stars, that could help explain the mismatch. But so far, no unambiguous evidence of population 3 stars has been confirmed. This isn't just a numbers game. If galaxies were already massive and organised so soon, it changes the timeline of cosmic evolution. It means that the first black holes, seeds of the supermassive ones we see today, must also have grown faster. It means that reionization, the process where the first stars and galaxies lit up the universe and ionized the hydrogen gas filling space, may have happened quicker and earlier. In short, it forces us to rewrite parts of the cosmic story. Another striking discovery is the variety of shapes. Webb's high resolution shows galaxies in the early universe that aren't just blobs. Some look like disks, some look clumpy but with ordered structures. Seeing that level of organisation less than 1 billion years after the Big Bang is like finding skyscrapers in a town that was just founded. The tension has already spurred debate. Some astronomers argue that Webb's data don't actually break cosmology, that once we refine our models of star formation and feedback, the numbers will fit. Others are more radical, suggesting we might need new physics or at least a new understanding of how dark matter and gas interact. The community is still sorting through the evidence, with more observations rolling in every year. But even with uncertainties, one point is clear. The universe is capable of building big, bright galaxies far earlier than we expected. That realization alone reshapes how we think about the first billion years. Webb hasn't just pushed our sightline deeper, it has pulled the cosmic dawn closer, showing us that the universe grew up faster than our textbooks allowed. And that was only the first category of surprises. Because once Webb showed us these ancient giants, it began finding other things that didn't fit. Strange chemistry, unexpected atmospheres, and odd signals from objects right here in our solar system. Galaxies growing too fast is shocking, but Webb's surprises don't stop at scale and structure. Some of its most puzzling findings come from chemistry, the fingerprints of molecules and elements written in light. Webb's infrared spectrographs can split light into its components and reveal what atoms and molecules are present in distant galaxies, comets, planets, and even dark interstellar clouds. What those fingerprints show is often stranger than anyone predicted. One striking example came in 2024 with interstellar comet 3, I/A TLAS. This object isn't from our solar system at all. It's a visitor from another star system, the second confirmed interstellar comet after 2I/Borisov. When Webb turned its spectrographs on Atlas, astronomers expected its chemistry to resemble the icy comets we know, with water vapour, carbon monoxide, and carbon dioxide in familiar ratios. Instead, they found something odd, an unusually high amount of carbon dioxide compared to water. The ratio was way off compared to solar system comets. That suggests the comet formed in a very different environment, perhaps farther out from its star where water stayed frozen, but carbon dioxide could condense. Why does this matter? Because comets are leftovers from planetary formation. Their chemistry records the conditions of the disk of gas and dust they formed in. If interstellar comets look chemically different, it means other planetary systems build themselves under rules that aren't identical to ours. Webb is literally sniffing the chemistry of alien solar systems by analysing chunks of ice that wander into ours. Then there's a discovery even closer to the boundary between planets and stars. In 2025, Webb identified a free-floating object only about 6 to 10 times the mass of Jupiter. It isn't orbiting a star, it drifts alone in space. Even more surprising, it has a disk of gas and dust around it, like a miniature protoplanetary disk. Webb's infrared instruments detected hydrocarbons in this disk, including methane and ethylene. These are organic molecules, basic building blocks of chemistry that, under the right conditions, could lead to more complex compounds. This raises fascinating questions. Are these lonely, starless objects forming planets of their own? Could moons condense around them, much as planets form around stars? We don't know yet, but Webb's ability to detect hydrocarbons around something that's small and faint is a leap forward. It suggests that the chemistry of planet formation might not be confined to the neat architecture of solar systems. The building blocks of complexity could be everywhere, even around rogue worlds drifting in the dark. Webb has also revealed new puzzles in the outer solar system. Take Makemake, one of the dwarf planets beyond Pluto. When astronomers used Webb to study it in mid-infrared, they expected to see a simple thermal profile, a cold, inert surface reflecting faint sunlight. Instead, they found an unexplained infrared excess. Something on or around Makemake was radiating more strongly than expected. One interpretation is internal heat. That would be strange, because an object that's small and distant shouldn't still be warm inside after billions of years. Another idea is a dust ring, debris orbiting Makemake, that absorbs sunlight and re-radiates in infrared. Either way, it suggests the Kuiper Belt is not the frozen, quiet graveyard it was once assumed to be. Even small, faraway worlds may be dynamic, with ongoing processes shaping their environments. Perhaps the most subtle but important chemical surprise comes not from a planet or a comet, but from a dark molecular cloud called Barnard 68. This is a cold, dense region where stars haven't yet formed. It's basically a stellar nursery still waiting for its first birth. For decades, astronomers assumed that cosmic rays, high-energy particles zipping through space, played a role in the chemistry of such clouds, exciting molecules like hydrogen. But the effect was never directly observed. Then Webb detected cosmic ray-excited H2 inside Barnard 68. For the first time, scientists had proof that cosmic rays are actively altering the chemistry of dark, starless clouds. This might sound like a technical detail, but it changes how we think about the origins of complexity in space. Cosmic rays may help kickstart the chemical reactions that build more interesting molecules, even before stars ignite. That means the raw material for planets and life may already be chemically primed long before a star system forms. Webb didn't just confirm a theory, it opened a window into how chemistry begins in the coldest places. Let's pull these threads together. What all these discoveries have in common is that Webb is showing us diversity and activity, where we expected uniformity and calm. Comets from other star systems don't share the same recipe as ours. Rogue worlds can host organic, rich disks. Distant dwarf planets may not be inert, but surprisingly active. Even dark clouds are chemically alive, stirred by cosmic rays. And each case has deeper implications. The chemistry of interstellar comets hints at planetary systems forming under different temperature gradients than ours. The hydrocarbons around a free-floating giant show that organic molecules don't require stars to exist nearby. The thermal oddities on Makemake suggest processes in the Kuiper belt that could revise how we model distant icy bodies. And cosmic rays in dark clouds emphasize that the universe's chemistry is never truly at rest. All of this feeds into the big picture. The universe is more chemically varied and dynamic than we thought. Instead of a neat progression, gas to stars to galaxies, with chemistry following predictable steps, Webb shows that processes happen in parallel, in unexpected places and sometimes far earlier than expected. And just as with galaxies, the chemistry puzzles are not isolated curiosities. They are forcing astronomers to reconsider long-standing assumptions. If comets can look wildly different depending on where they form, maybe our solar system is not typical. If rogue objects can host organic-rich disks, maybe moons and planets can form in environments we never imagined. If dwarf planets can stay warm or host dust rings, maybe activity is common even at the edges of solar systems. And if cosmic rays can seed chemistry in starless clouds, maybe the raw ingredients for life are distributed more broadly and earlier than anyone thought. What Webb is teaching us here is humility. The universe doesn't stick to our categories. We like to think of planets forming only around stars, of comets having predictable compositions, of icy dwarfs being inert, and of chemistry waiting for stars to switch on. But Webb's infrared eye is showing us that those categories were too narrow. The cosmos is experimenting with more variations than we gave it credit for. And just when we thought these surprises were confined to the distant universe or the edges of our solar system, Webb pointed at familiar giants closer to home and found strangeness there too. When people think about the James Webb Space Telescope, they usually imagine it peering into the distant universe, galaxies forming near the dawn of time. But Webb is also turning its infrared eyes on objects much closer to home, right here in our solar system. And the results are every bit as strange as the ancient galaxies. Some of the biggest surprises have come from places we thought we already understood. Saturn, Pluto's moon Charon, and other icy bodies at the edges of the sun's influence. Take Saturn. It's been studied for centuries with telescopes, and up close by spacecraft like Cassini, which orbited it for more than a decade. By now you'd think we had its atmosphere mostly figured out. Yet when Webb observed Saturn in 2023 with its near-infrared camera, astronomers saw something that didn't fit any existing model. Mysterious dark beads scattered in the planet's upper atmosphere. These spots appeared like tiny punctures or voids in the infrared glow, almost as if something was blocking light in very specific regions. To make things stranger, Webb also caught a lopsided star-shaped pattern at Saturn's north pole, an irregular brightness that scientists had never seen before. So what are these beads? No one knows yet. They could be linked to complex dynamics in Saturn's upper haze, or to chemical reactions producing aerosols that absorb infrared light in unusual ways. Another possibility is wave patterns in the atmosphere, creating regions of different densities. Whatever the explanation, the fact that a brand new telescope spotted features missed by Cassini, a spacecraft that was practically living at Saturn, shows just how sensitive Webb is in infrared. It can catch subtle signatures invisible to cameras tuned to visible light. Moving farther out, consider Pluto's largest moon, Charon. It's about half the size of Pluto, and so large relative to its host that some astronomers call the Pluto-Charon system a double dwarf planet. For decades, Charon was thought to be geologically dead, an icy rock orbiting in the cold with no atmosphere to speak of. But Webb's spectroscopic observations in 2024 overturned that assumption. Webb detected frozen carbon dioxide and hydrogen peroxide on Charon's surface. Both are surprising. Carbon dioxide ice sublimates easily in sunlight, so seeing it on Charon suggests some process is replenishing it, perhaps internal outgassing, or chemical reactions driven by radiation. Hydrogen peroxide is even more intriguing. On Earth, it's a reactive molecule that doesn't last long unless constantly produced. On Charon, its presence points to energetic processes, likely from radiation bombarding water ice and splitting molecules apart. That means Charon's surface is chemically active, even in the deep freeze of the Kuiper belt. These findings challenge our picture of outer solar system bodies as inert relics. If Charon is actively producing new compounds, it may not be unique. Other moons and dwarf planets could be undergoing similar radiation-driven chemistry. Over billions of years, that chemistry might create complex molecules, potentially even prebiotic ones. Webb isn't telling us that life exists out there, but it is showing us that the outer solar system is chemically restless, not frozen in time. Another Webb target was Makemake, one of Pluto's neighbours in the Kuiper Belt. As mentioned earlier, Webb picked up an unexplained mid-infrared excess coming from the system. Some researchers suggest this could be a thin dust ring orbiting the dwarf planet. If confirmed, Makemake would join the shortlist of small solar system objects with rings alongside Chariklo and Haumea. Rings are usually associated with giant planets like Saturn, but Webb hints they may be more common than expected, even around small icy worlds. If that's the case, it raises questions about how such rings form and persist in low-gravity environments. These discoveries point to a bigger theme. The outer solar system is far from a static museum. It's more like a laboratory, where radiation, chemistry, and dynamics are constantly reshaping surfaces and atmospheres. Webb, with its infrared sensitivity, is the perfect instrument to reveal that hidden activity. But Webb hasn't only looked outward, it's also helping refine what we know about our solar system's gas giants. Besides Saturn's dark beads, Webb has probed Jupiter's atmosphere. Studying auroras and the distribution of gases like methane, it has captured images of Uranus and Neptune, revealing details about their faint rings and hazy atmospheres. Even in these closer studies, Webb often sees unexpected structures, temperature contrasts, cloud bands, or chemical distributions that don't match models built from Voyager flybys or Earth-based telescopes. What ties all of this together is the reminder that we don't fully understand even the worlds in our backyard. For years, planetary science treated the outer solar system as a slow, frozen domain, but Webb is showing us otherwise. There are active chemical processes on icy moons, unexplained features in giant planet atmospheres, and possibly even rings around dwarf planets. Each of these discoveries forces scientists to revisit assumptions that were considered settled. And in a sense, this is the same story as with the distant galaxies. In both cases, Webb reveals complexity earlier, or closer, than we thought possible. Galaxies grew up faster, and solar system bodies are more dynamic. The telescope's strength isn't just in seeing farther, it's in showing that reality is richer than our simplified models. So what does it all mean? It means that science is entering a new phase where even familiar territory can surprise us. Saturn's atmosphere still holds mysteries. Charon is chemically active. Makemake might have a ring. These are reminders that exploration doesn't end just because we've sent spacecraft past these worlds. A new instrument, with a new way of seeing, can still turn up the unexpected. And the implications ripple outward. If our solar system is more active and varied than we assumed, maybe other planetary systems are too. The odd chemistry of comets, the hydrocarbons around rogue objects, the strange activity of dwarf planets. All of these findings suggest that planets and moons elsewhere in the galaxy may also be full of surprises. With Webb, the universe doesn't just look bigger and older, it looks weirder, in ways both close to home and unimaginably far away. By now it's clear that the James Webb Space Telescope is not just handing us pretty pictures, it's shaking up the foundations of astronomy. The galaxies are too big, the chemistry is too strange, and the solar system is more active than expected. Each of these discoveries forces theorists to step back and ask, are our models wrong, incomplete, or just missing critical details? Let's start with the early galaxies. For decades, simulations of the universe followed a pretty stable recipe. Take the Big Bang, add dark matter halos, sprinkle in gas that cools and collapses into stars, and then watch galaxies grow through mergers. The timeline was always thought to be gradual, tiny proto-galaxies at first, slowly building into structured spirals, and ellipticals over billions of years. Webb blew a hole in that neat sequence by showing that within just a few 100 million years, some galaxies were already massive and bright. The challenge here is not about whether the Big Bang happened, the evidence for that remains overwhelming, but about the details of structure formation. If galaxies can assemble stars that quickly, then our understanding of star formation efficiency may be off. Perhaps gas in the early universe collapsed more readily than expected. Maybe the feedback from supernovae and black holes, which should blow gas back out and slow star growth, was weaker in those times. Or maybe dark matter itself doesn't behave quite the way we assume. Some researchers have suggested that dark matter might have self-interactions, tiny collisions or exchanges of energy that make it clump differently. If true, that would fundamentally alter the backbone of galaxy growth. Then there's the issue of black holes. If galaxies grew faster, their central black holes likely did too. Webb has already spotted signs of massive black holes in galaxies less than 1 billion years old. But how did black holes get so big, so fast? The standard idea is that they form from collapsed stars and slowly accrete matter. That takes billions of years to reach millions or billions of solar masses. Yet Webb shows us black holes that seem to have bulked up in record time. One possibility is that some black holes started bigger, forming directly from collapsing gas clouds rather than stars. Another is that early conditions allowed runaway growth we hadn't accounted for. Either way, the existence of giant black holes in the early universe complicates our neat models. Now shift to chemistry. Webb's detections of unusual molecular signatures, like the carbon dioxide-rich interstellar comet or hydrocarbons around rogue worlds, show that planet formation is more diverse than we thought. For decades, scientists assumed our solar system was a good template for others. Comets here have a certain balance of water, carbon monoxide, and carbon dioxide. Planets form in disks around stars. Dwarf planets are inert. But Webb is breaking that template. The implication is that we can't assume all planetary systems follow our script. If comets form with wildly different chemistries depending on their star's environment, then the delivery of water and organics to rocky planets could vary enormously. That means some exoplanets might start out with oceans of exotic mixtures, while others might be bone dry. If rogue objects can carry organic molecules without even orbiting stars, then the raw materials of complexity are scattered more widely across the galaxy than we realized. Even the findings in our own solar system raise theoretical headaches. Saturn's dark beads show that we don't fully understand giant planet atmospheres, despite decades of spacecraft data. Charon's hydrogen peroxide suggests radiation chemistry is active in ways not accounted for in surface models. Make's infrared excess hints at hidden heat or a dust ring, either of which rewrites our assumptions about small icy worlds. Each of these forces planetary scientists to refine their understanding of how atmospheres, surfaces, and interiors behave under extreme conditions. And then there's the discovery of cosmic rays exciting hydrogen in dark clouds. That sounds niche, but it has big implications. For years, models of star formation assumed that chemistry in dark clouds was relatively quiet until stars formed. Now we know cosmic rays are constantly stirring the pot, kicking off reactions even before the first stars light up. That means the building blocks of more complex molecules could be forming earlier, in more places and in greater abundance than expected. It suggests that prebiotic chemistry, the kind that eventually leads to life, might not need to wait for stars and planets. It might start in the dark. Put all of this together, and you see a pattern. Webb is exposing cracks in our predictive power. Our simulations and models worked well enough with the data we had before. But Webb's new sensitivity is revealing details those models can't explain. That doesn't mean the models are useless. It means they need updating. Science advances by confronting anomalies, and Webb is serving up anomalies by the dozen. But this comes with challenges. First, not every strange observation means new physics. Sometimes the simplest explanation is an observational bias. For example, maybe some of the too bright galaxies are boosted by gravitational lensing, making them appear larger than they are. Or maybe their stars are different kinds, extremely massive and short-lived, giving off more light per unit mass. Distinguishing between genuine theory-breaking discoveries and misinterpretations takes time, careful analysis, and more data. Second, theory has to keep pace with observation. Right now, teams around the world are scrambling to update cosmological simulations to match Webb's results. That means adjusting star formation recipes, feedback mechanisms, and dark matter behavior. But even supercomputers have limits, and building simulations that match reality in detail is enormously difficult. Webb's surprises have raised the bar, and theorists are still catching up. Finally, there's the philosophical challenge. Many of us like the idea that the universe runs on neat, predictable rules. Webb is reminding us that reality can be messy. Galaxies may form faster than expected. Chemistry may take unexpected routes. Planets and moons may be more active than our categories allow. These aren't failures of science. They're reminders that nature is under no obligation to match our expectations. The exciting part is that Webb is not shutting down theories, it's opening them up. If dark matter needs tweaking, that could point us toward new physics. If black holes form differently, that could reveal overlooked processes in the early universe. If chemistry is more varied, that expands the possibilities for habitability. Every puzzle is an opportunity to refine our understanding, to replace a too simple model with one that captures more of reality. And we're only a few years into Webb's mission. It's designed to last at least a decade, and possibly much longer. That means the surprises are likely to keep coming. Today's anomalies may be tomorrow's breakthroughs, the seeds of entirely new fields of astrophysics and planetary science. If there's one thing the James Webb Space Telescope has taught us so far, it's that every new image comes with surprises. But Webb is just getting started. It was launched in late 2021, fully commissioned in mid-2022, and it has enough fuel and stability at the L2 point to operate into the 2040s. That's decades of discovery ahead. The obvious question is, what will astronomers do with all that time, and how will future instruments extend Webb's reach? First, Webb itself still has a lot of unfinished business. One of its main goals is to map the earliest galaxies with greater precision. Right now, many of the too big, too bright galaxies are based on redshift estimates from photometry, measuring the colour of light across filters. To confirm those distances, Webb needs to take detailed spectra, which give much more accurate redshifts. That's happening now through large survey programs. In the next few years, expect firmer answers about whether some of these galaxies really are as old and massive as they appear, or whether they're tricking us with unusual star populations or lensing effects. Webb will also probe the chemical fingerprints of those galaxies. By looking at the emission lines from hydrogen, oxygen, and other elements, astronomers can measure metallicity, the abundance of elements heavier than helium. That tells us how many generations of stars have lived and died in these galaxies. If young galaxies are already rich in heavy elements, it means star formation and supernovae were happening faster than expected. If they're poor in metals but still bright, it might point to exotic early stars, unlike anything we see today. Closer to home, Webb will continue dissecting exoplanet atmospheres. Already it has made headlines by detecting carbon dioxide, water vapour, and even hints of methane in planets orbiting distant stars. Over the next decade, Webb will target smaller Earth-sized planets in habitable zones of red dwarfs. The goal isn't to find life directly, that's beyond its capability, but to search for combinations of gases that can't easily be explained without biological processes. Even ruling out simple scenarios helps narrow the hunt. Webb is essentially writing the first detailed catalogue of exoplanet atmospheres, a dataset that future telescopes will build upon. Speaking of future telescopes, the Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will complement Webb. Roman won't match Webb's infrared sensitivity, but it has a much wider field of view, about 100 times larger. Where Webb zooms in on tiny regions of sky, Roman will scan vast swaths, producing cosmic maps that can locate targets for Webb to study in detail. Think of Roman as the wide-angle scout and Webb as the close-up investigator. On the ground, the extremely large telescope, ELT, in Chile, set to begin operations late this decade, will provide another crucial piece. With a 39-metre mirror, it will dwarf Webb's size and deliver incredible resolution in visible and near-infrared. Its adaptive optics will counteract Earth's atmosphere, letting it zoom in on galaxies, star clusters, and exoplanets in ways Webb cannot. Webb will often point the way, identifying strange targets, and the ELT will follow up with detailed spectroscopy. Looking farther ahead, NASA is already considering Webb's eventual successor, a mission sometimes referred to as Habitable Worlds Observatory. This telescope would be optimized for directly imaging Earth-like planets around Sun-like stars, something Webb isn't designed to do. It could launch in the 2040s, building on Webb's discoveries by targeting specific star systems where conditions for life seem most promising. But even before those new observatories arrive, Webb itself has plenty of uncharted territory. For example, its surveys of star-forming regions are just beginning. Already, Webb has imaged places like the Orion Nebula and the Carina Nebula, peeling back clouds of dust to reveal newborn stars and protoplanetary disks. Over time, These surveys will let astronomers trace how stars and planets form step by step. Combined with the chemistry data from comets, rogue objects, and dark clouds, this could rewrite our understanding of where the ingredients for planets and life come from. Another frontier is time domain astronomy. Webb isn't just a still camera, it can monitor changes. That means tracking the weather on giant exoplanets, watching storms on Jupiter, or monitoring variable stars in distant galaxies. By repeating observations months or years apart, Webb can build movies of cosmic activity. This is something Hubble did occasionally, but Webb's infrared vision reveals processes invisible to visible light telescopes. And let's not forget our own solar system. Webb will continue observing Saturn to see if those dark beads change with seasons or storms. It will map the composition of more Kuiper belt objects, testing whether Make's strange infrared excess is unique or common. It could even help study interstellar visitors like 3I/ATLAS in more detail, or detect the chemistry of new comets as they swing through. For planetary science, Webb isn't a replacement for spacecraft, but it's a powerful complement, providing spectral data no probe could gather so far from Earth. Each of these efforts builds toward a bigger goal, refining the story of the universe from the Big Bang to today. Webb's first few years reveal cracks in the narrative. Galaxies forming too quickly, chemistry running ahead of schedule, and planets and moons more active than expected. The next decade will be about filling in those cracks with data, figuring out which surprises are genuine rule breakers and which are quirks of observation. The most exciting part is that we don't know which direction the evidence will point. Will early galaxies force a rethink of dark matter physics? Will comet chemistry show that planetary systems come in wildly different varieties? Will Webb stumble onto an exoplanet atmosphere that raises eyebrows about habitability? Each possibility would be transformative, and the universe is vast enough that Webb will likely deliver shocks we haven't even imagined yet. When Hubble launched, no one expected it would uncover dark energy or reveal galaxies assembling in the early universe. Webb is already ahead of schedule in that regard. It's not just filling gaps, it's opening new chapters. The James Webb Space Telescope was designed to extend humanity's vision into the infrared, to look farther and fainter than anything before it. In just a few years, it has already redefined what farther and fainter mean. But the real story isn't just about seeing deeper, it's about what we found once we looked. Instead of faint, primitive galaxies slowly blinking to life, Webb showed us massive, structured ones appearing shockingly early. Instead of inert comets and quiet dwarf planets, it revealed chemistry that doesn't fit our expectations. Carbon dioxide-rich interstellar visitors, hydrocarbons circling lonely rogue worlds, and icy moons with surfaces alive with radiation-driven processes. Instead of silent dark clouds waiting passively for stars to form, Webb found cosmic rays stirring chemistry in the cold. And even in the solar system's most familiar giants, it spotted features like Saturn's mysterious dark beads that no spacecraft had ever noticed. Every one of these discoveries points to the same conclusion. The universe is richer, more active, and more surprising than our models predicted. Our theories weren't wrong so much as incomplete. They were built from the limited data we had before, and Webb is exposing their blind spots. This is how science works at its best. New tools push into new territory, and the universe pushes back with puzzles. Each puzzle forces us to adjust our story of cosmic history. Galaxies formed faster. Then star formation must be more efficient, or dark matter must behave differently. Chemistry is more diverse. Then planetary systems may follow many different recipes, some leading to exotic outcomes we haven't imagined. Icy worlds are more active, then the outer solar system isn't a frozen graveyard, but a chemical workshop still running billions of years after formation. And beneath all these specifics lies a deeper theme. The universe does not wait for us to catch up. It is under no obligation to follow the categories we've built or the timelines we've assumed. Webb reminds us that we are still early in the process of figuring things out. Just as Hubble forced us to accept that galaxies assembled faster than we thought in the 1990s, Webb is forcing us now to confront even earlier surprises. What makes Webb different is its reach. It's not just a telescope, it's a bridge across billions of years. The light it captures set out before Earth even existed, before the sun had formed, when the universe was still in its infancy. And yet when that light finally arrives and Webb records it, it doesn't show us a simple beginning. It shows us complexity. Galaxies already shining, chemistry already diverse, worlds already dynamic. So the big question isn't just what Webb will see next, but how much of our cosmic narrative will need rewriting? Are these early galaxies rare outliers? Or is the universe as a whole much more efficient at building structure than we believed? Are rogue worlds with organic disks common, making the building blocks of life widespread across the galaxy? Are dwarf planets and moons active in ways that make our solar system look ordinary instead of unique? The truth is we don't know yet, but we're watching the answers unfold in real time. Webb has decades ahead to keep probing, and other telescopes will join in, each extending our reach in different ways. Together they will piece together the story, not the neat, orderly one we expected, but the messy, surprising, and far more interesting one that nature is writing. In the end, the most shocking thing Webb has found isn't any single galaxy, molecule, or planet. It's the reminder that discovery never stops. Every time we think we've seen far enough, there's something waiting just a little deeper, daring us to look again.